Right, so looking at the next question on the worksheet, this is problem number 8. You see that you're given a curve presented in parametric form, and in part A, you're asked to compute the derivative dy dx. So in this video, we're going to see how we can compute derivatives for curves presented in parametric form, and then in the next two videos, we'll go ahead and apply the results. All right, so let's say we have this curve C in the xy plane, and this curve is described by the equation y equals f of x. And we want to compute the derivative at this point P. Okay, so in other words, we're going to compute the slope of this green tangent line here to the curve at the point P. All right, now if we have a parametric representation for this curve C, so our tracing point will move along C in the direction indicated by these arrows as the parameter T increases. Well, y is a function of x, and x, it depends on t. So what does the chain rule say in this context, right? Y is a function of x, and x is a function of t. And so through composition, y depends on t, right? So put another way, if I increase t, this will affect x, and affecting x will in turn affect y. And so if I increase t, I will have affected y, right? Y is a function of t. And the chain rule says that the rates of change for these various dependencies can be related as follows. Okay, the rate of change of y with respect to t, so this is dy dt, is equal to the product of these two intermediate rates. So it's equal to dy dx times dx dt. Okay, now if I want to know dy dx, and I know that dx dt is not 0 at a certain point, then I can divide both sides of this equation by dx dt, and that leads me to the following key result. Okay, so dy dx is equal to this ratio of dy dt to dx dt, and this holds provided dx dt is not 0. Alright, so the nice thing about this result is that if I have a curve presented in parametric form like I do in problem 8, I can compute dy dx entirely in terms of the parameter t. That's what this right-hand side allows me to do. It says take the derivative of the y function with respect to t and then divide that result by the derivative of the x function with respect to t, and you got it. Alright, so now before we finish up here, there's a couple more things to add. So first off, if we're at the point P, note that if I increase x, this incremental amount dx, then y, in this case, will rise up along this green tangent, this amount dy. And the ratio of dy to dx, in other words, the derivative of our function at the point P, gives us the slope of this green tangent, right? This is just a fundamental result in Calc 1. All right, so now, if I consider this picture just down here, what I want to look at is what happens if I take dx and dy and divide them by dt. Well, you want to think about dt as a small quantity, so think about it as, say, a millionth. Okay, if I divide these lengths by a millionth, well, that's going to stretch them out, right? And since we're dividing these lengths by the same amount, the stretch factor is the same for both. And so we get these two new lengths, and again, since the stretch factor is the same, we have a pair of similar triangles. And so dy dx, that's the left-hand side, is equal to, since the triangles are similar, to the ratio of dy dt to dx dt. That's the right-hand side. Okay, so it's a way we can think about this result geometrically. Now, if I'm thinking about the motion of this particle along our curve C as described by the parametric equations, well, what's dx dt tell me about that particle? It tells me the rate of change of the particle's x-coordinate with respect to t. So in other words, it's the particle's horizontal velocity. And likewise, dy dt, that's the rate of change of the particle's y-coordinate with respect to t, that's the particle's vertical velocity. Okay, and so yet another way to interpret this result is to say that dy dx, which is the slope of this green tangent, is equal to the ratio of the particle's vertical velocity to the particle's horizontal velocity. And this will hold provided the horizontal velocity of the particle is not 0. All right, so the last thing I want to address is what happens if dx dt, in other words, the horizontal velocity is 0 at a point. What can we say then? Well, if dx dt is 0 and dy dt is not 0 at a point, then the curve C will have a vertical tangent at that point. So to illustrate, I've drawn this curve here. So as the parameter t increases, our particle moves along the curve in the direction indicated by these arrows. And see, at the point P, dx dt equaling 0 implies the x-coordinate is not changing at this one instant. So in other words, right, we're not moving in the horizontal direction, so neither to the left or to the right at this one instant. There's no horizontal component to the particle's velocity. Okay, now the way I've drawn this picture, since the particle is rising up, dy dt is positive in this case. But the point is, right, if dx dt is 0, so the horizontal velocity is 0, but the vertical velocity, dy dt, is not 0, then you only have vertical motion at that one instant, right? You have a vertical tangent. Okay, well, that's a good place to stop. In the next 2 videos, we will look at questions 8 and 9 that will illustrate all this stuff. All right, I'll see you there. Thanks.